Okay, so today is lecture 8, and we're going to talk about kNearestNeighbor. And this is a transition class because kNearestNeighbor can be used for both regression and classifier. So that's why I'm picking this specific algorithm as kind of finishing wrap up the regression section and starting the classification section. All right, so okay, so again, so let's just look at our nutshells. And in terms of kNearestNeighbor classifier, it's, as I said, it can be used for regression and classification. So that's why in the task, that task module, it really depends on what's your data, what's the target variable you care. And it has this intrinsic local smoothness assumption as the representation. I'm going to talk about what do I mean local smoothness in next few slides. And kNearestNeighbor based algorithm, in fact, minimize something called expected prediction error using the L2 specific kind. And it's predicting the conditional mean, but the derivation is just too hard, and I skip it and I put it in extra slides, both in this lecture and also in the next lecture. So if you're interested, feel free to check out those extra slides. And there's no search or optimization, at least in the naive version, the vanilla version of kNearestNeighbor predictor. And its model, it's very interesting. So there's no parameters here. The vanilla version, the parameter, the whole parameter, the model is just the set of training sample themselves. All right, so let's use a concrete example to show you what is kNearestNeighbor regressor. So we are given this example, just this one-dimensional X input and then Y output. We actually had very similar this type of problem before, and we solved it, used this RBF-based regression model. So for this one, we instead using, like, we don't do assumptions at all, no assumptions here. I'm just trying to predict the predictor Y for a given X, for a new X, and using its neighbors. So what do I mean neighbors? So for every nearest neighbor approach, you have three things in your when you need to perform this algorithm. The first is you need to have a set of training samples. So in this case, it's just the xi and yi pair. So that's just your training. And this is actually your model. And there's no training at all. There's no learning phase. The second thing you need to know is how many neighbors for a future point you need to consider. So that's called k, like k, just k nearest neighbor. So assuming in this task, we just assume is k equal to 5, and k is picked by the users of kNearestNeighbor. And in this case, I just select a 5. And the third thing is, so how do you decide a future point is a nearest neighbor for the other point? How do you calculate that distance measure? So in this one, it's actually extremely simple because it's just R, right? We're just going to use absolute position differences of my future points versus the training point, and to figure out who are my nearest neighbor. So in this case, it's actually very, very simple. It's in fact, it's just Euclidean distance in the R space, in the R1 space. So let's assume there's a future point, maybe here. So this is my X question mark. And how could I know its nearest neighbor? So it's actually very simple. I just go to C, because you just look for all the possible xi in your training data, and who are the 5 nearest for my x question mark. And even so, for this extremely simple case, you just eyeball, right? So very clear, my nearest neighbor is, so this point, and this point, and that point. And I think, let's look at for the distance of this versus, yeah, so this is my first neighbor. So it's a little bit tricky to figure out the fifth one. So on the right, it's absolute differences because this is my x question mark. And I think the nearest neighbor is actually this one. So, and then I'm going to predict for this specific points, the y as the mean of this 5 points. So roughly, and then you're just going to check out the y, right? So what are the mean of this 5 points y? I think roughly it should be here. So let me use a different color then to show the predicted. All right, I cannot change color. Okay, let's just keep using this color. So I think the y of this one is roughly here. So this is my predicted y. This is the y predicted. Then you can just do really the similar things for every possible point in our space and to know who are the nearest neighbors. And I think this point may be my nearest neighbor. So again, this 3 plus this new one. And then based on the distance measure is this point or this point. I think it's more like this point. So this point will have a little bit higher measure, higher predicted y. So, and then you just do for every point, and I think it's going to get, so always like, yeah, it's highly likely to get something like this on the right, and then on the left, I mean, you just keep doing this nearest neighbor operation again, and then until you feel you can predict for every point in the R, and based on the training data, what are the predicted y. So this is just as simple as it really like this. It's called, I think it's maybe like this. Yeah. I think for this here, maybe the boundary point in this kind of regression model, it's actually pretty tricky. So yeah, maybe like, and then it's very related to the last point in your boundary point, and those everything will be predicted, I think, according to that boundary point. It's not like as dramatic as what I had, but I think it's most likely will be like this. Yeah. All right, so this is I show you, I'm handily making this regression. So now I'm going to show you a code run from the one Jupyter notebook I made. Okay, so I already shared the link to everyone already. So in our slide, you can actually run it. So so first, again, you just load the library, and this is a very concrete data. Actually, this time I'm using, it's called Boston housing dataset, and what we're predicting is this feature 14, which is the mean value of this owner-occupied home. It's just you're predicting the house price. And we just load this data. It's scikit-learn data. I mean, it's very easy, just one command, you can load it. And after you load the data, so because I want to make you, so there are 13 features in this data, but I want to show you just one dimensional because that can be visualized. So I'm just picking the 5th feature. And I think the 5th feature is this, more this feature. And this is what you're going to get, and if you visualize it. And so maybe some of you feel very weird when in our homework we give you something like a 2 feature. We actually had a pseudo feature in our given files. The reason was actually because you can directly read from the data, then you can directly start to write, and they'll also use those like scikit-learn library if you want to check if you did correctly. And if you want to use the scikit-learn libraries, you need to guarantee that's a 2-dimensional matrix form. And this, we try to avoid this function. It's not that very apparent, so that's why we just give you already the pseudo feature. It's already given in that file to avoid the mistakes. So for those of you who actually knows about it, hopefully understand why we give you the data like that. But it's totally actually not necessary, that pseudo feature. Yeah, it's just for your coding. It's easier, to avoid the potential mistakes. All right, so let's just load the kNearestNeighbor regressor. And same thing, you just feed the model, and then there's only one parameter I just told you, right? So when you're trying to use kNearestNeighbor, the only thing you need to have is the training data plus a k. And in this case, I'm picking a really large number, actually 100, and I'm feeding the model. So in the vanilla version of kNearestNeighbor, actually this just does nothing. And then, so I'm actually feed my model on all of that training data. I did not even do the training test split. It's just to show you, because I can eyeball if that's good or bad for the future points. All right, so now I'm just using all of the possible x from a range 3 to 10, and I'm trying to fit it. And it's just this pretty smooth line, and this is my regression prediction based on that feature input. So now let me change this to 5. Again, the same regression model, and this time this is what we get. So keep this in mind. When k is really small, we got a super wiggling regression model. When k is super large, you can also try 200 or maybe even even larger. You got a super smooth regression model. So k small, the model is much more flexible. K large, the model is super smooth. All right, so keep this in mind. So I then want to show you something we actually show you in the second class about the 2 modes of machine learning. And I hope you still remember, this is that very easy digit classification task. And we have 2 modes. I have train and test. We use support vector machine classifier. And this time we just change it to a kNearestNeighbor classifier. Very easy. And you predict, and every step is the same. The only thing you changed is the kNearestNeighbor classifier. So you again pick the nearest neighbor. That's your most important one of the hyperparameter to pick, and you predict classifier.fit, and then again on the x train and y train. Then you predict on x test, and that's this gives you the performance on the future data, which is pretended by the x test. So let's see this performance. This is the matrix you get. It's actually very, very good. 0.96 the accuracy, and this is, I think, the accuracy, and then almost everything is 96, and that's compared to that SVM classified model, which uses the RBF, which is the state of the art when you have medium large of training data, and this gives you a little bit better results. So the whole thing I try to show you is just kNearestNeighbor, in fact, is extremely simple, but also a powerful method. Okay, so let's now come back to my slides. Okay. All right, so Sorry, I'm looking for my pointer. All right, okay. I think I can. Oh, it's right here. Okay, so so this is just the code run, and then to show you, I mean, the K actually matters, and K small, the model is more flexible. All right, so let's come back this to the nutshell view, and let's just dive in more details of kNearestNeighbor method. So what is the representational assumption of kNearestNeighbor? In the end, it assumes the future points are very similar. The future points target value, it's very similar to this future point's neighbor's target value. That's the basic assumption, which is we summarize the term like called a local smoothness. I'm very similar as my neighbors in terms of that target output. Okay, so again, so it can be used for regression when the target y is numerical, and we showed you this example. Oh, this is actually a little bit different from, yeah, I think this is more correct because, yeah, let's see this point because it will influence by all the 5 members, right? So for all the future points within, so for every future point here, if you want to see the kNearest neighbor, it always will be this 1, 2, 3, 4, and 5. So which means it always will like starting from, if you don't have like more points on the left than this first point, everything on the left will be predicted roughly close to the y2. Yeah. All right. Okay, so then let's take a look at when your task is classification task. So when your task is classification, so in this case, we actually saw this before, just assuming you have this, the internet like web document, you represent them into a bag of words, a vector space representation. In this case, it's extremely simplified. There's only 2. So this is like 2-dimensional. Let's just assume this is x1, this is like x2. And then there are 3 classes: sports, science, and arts. So when you have a future point, and how do you decide? Again, so you look at this future point, the distance against all the training data, and then you have to calculate that distance versus all the training data. So you just do this calculation to all the possible training data, to each one of the training data, and then you got a distance matrix, metric number, then you sort them, then you got the kNearest neighbor, assuming this time we just do k equal to 5, and you use, you can just use the majority vote of your neighbor's class as the predicted class. So in this case, it will be red because there are 3 red versus 2 blue, and there's no darker blue or black color. So this is extremely simple, right? But you can actually tell already what is the issue of this type of models, and we're going to talk about it later. It's actually about computational time cost. So keep that in mind. So what is the procedure to look for nearest neighbors? The reason why I can get a nearest neighbor is because this is extremely simple. I can just eyeball who are my neighbors, right? When you're in the high-dimensional p-dimensional space, how could I even know when there's a future point who is my nearest neighbor? And you really just have to calculate the distance among the future points, every future point versus every training point. And that will be expensive. Okay, so now let's see, just kind of repeat what I said in the simple examples. So kNearestNeighbor approach, it's one kind of instance-based algorithm. So I will talk about more about instance-based algorithm in the second module. So just give you this terminology first. So this type of instance-based method, they need three things. The first is a set of stored training samples, and so training samples, and they are seen as a set. And the second is it needs to know what are the metric function, distance metric function that you can use to compute your future point versus the training point. So what is that metric? And the third is what k? How large is the neighbor you're going to consider? So there are actually different kinds of nearest neighbor definitions we're going to talk about later. All right, three things in k-nearest neighbor. And then let's see, what's the training mode of k-nearest neighbor? In fact, in the vanilla version, you do nothing in the training mode because there's nothing need to be decided, right? So for every training point, you know their labels. There's nothing to be learned, and that's it. So it has no cost in training. And then let's see in the testing or deployment mode, when there's a future point coming in, and for every point, for example, that's the X question mark, like I repeated saying, I need to calculate this X question mark versus my first training data versus my second training data until my X, assuming N is the training size, I need to calculate this first. And after I get this, I need to do a sorting. So step 1, distance calculation. Step 2, sorting. And then step 3 is this to make Y question mark prediction. What is it? So that's the 3 steps. All right, so step 1, compute distance to all the training records. So this is just in the vanilla version. As I try to emphasize again, this is computationally expensive. And the state-of-the-art k-nearest neighbor has a lot of tricks to avoid compute future points to all the training records. And there's a lot of something called KD tree-based data structure to help you avoid computing to all the training points. And you, based on property of the future point, you need to calculate that distance to only part of the training records. So those are more advanced k-nearest neighbor method. But in the vanilla version, you need to compute the distance of each X question mark to all the training points. And then you sort and to get k-nearest neighbors, and then you just use the vanilla version, you just do majority vote, use the class labels of nearest neighbor to determine the class label of on a record. So again, so what is my assumption again? My assumption is I am similar to my neighbors. To my k-nearest neighbors. So which means this local ball has all the same class. This is what we meant, local smoothness. The smoothness is with regard to the class labels. In the classification case, it's class labels. In the regression case, it's the regression values. Local smoothness. All right, so let's again see one more example. So when you have a question mark, you see in this case, you're going to predict the S block. Sorry, it's a little bad animation, but okay. So when you have K larger, you're going to predict this as yellow. So this points as yellow. So now I want to do a time cost computation. So we already talked about this whole procedure, right? So let's see what's the time cost. So step 1. So I'm having a X question mark, so I'm going to use samples as S question mark, right? So that's just showing it's a sample. So assuming this is like there are n samples, and this is like x1 to x6 features, x3 features. So this is like p feature. Let me use like vector shape to represent this. I can use S, just make it easier. Okay, so the first step, I have the sample as question mark. So when I'm calculating the distance of this I versus the S question mark, this is a p-dimensional vector. This is a p-dimensional vector. So what is the cost to calculate this in using Euclidean distance? You can type in chat. So Euclidean distance or inner product distance. So when you calculate the vector versus another vector in terms of Euclidean distance or in terms of the inner product distance or cosine distance, so what is the time cost? Please type in the chat. So this is your features, x1, x2 onto xp, x1 onto xp, and inner, yes, it's actually OP, correct. Yeah, the cost to calculate that distance, not versus all the n samples, only just a pair. My S question mark sample versus A sample. Let me put that as S1, yeah, S1 sample. Yeah, so this, in fact, it's OP, right? Because no matter it's inner product or it's Euclidean distance, you normally need to do a calculation among feature and feature. You have a total of p features, no matter it's minus take a square or it's multiplication, and you take a summation over all the values. So assuming that's use inner product, but if you do inner product, that's similarity, right? So you need to be aware how to convert that into distance. So let's just keep it like the distance. So distance is more like this. X, like I minus X. I should use J just not to get you confused. J from 1 to P and take a square, and this is actually OP cost. All right. So now because I need to do this for I need to do this for all the samples, right? So it's like the S1 versus X question mark, the S2 versus X question mark, and onto all the training data, X question mark, S question mark. So this gives me OMP cost. All right, so this is step 1. And then step 2. Step 2, I have to look for the nearest neighbor, which equivalent to what? Just like I already tried to see this. You do the sorting of this distance measure. You try to get top k out of n. I hope you still remember from your algorithm class. What's the cost of this? Please type in chat if you know. Let's just do a naive version. Yeah, I think you can do ON. Actually, not totally. There's need to be a little bit smart choices, but let's just put ON there. It's also related to the K. Yeah, but I will do, I'm abusing the term a little bit. Yeah. So, okay, so you can actually see, yeah, it's actually n log n. That's true. It's, yes. So, but it's also related to the K. It depends on what type of data structure you use. So, yeah, all right. Depends on what algorithm you use. I mean, yeah, I should put log n there. Yes, let's be a little bit more precise. Yeah. All right. So okay, so you can see this, and this is only for one sample. Assuming I have m samples, I have m testing samples, m test, and this is m. This will be m's times that np and m's times that n log n. And actually, you can do a little bit faster than this n log n, but let me just put a naive version like to here. All right. Okay, so this is actually extremely computationally costly. And also the bad thing is, the more you use this algorithm, the more costly. So this is what we call what? This means it's computationally very heavy in the inference stage or in the deployment stage. So this is another, it's almost a repetition of the previous page, so I will not need to, it doesn't need to be repeated. Okay, so let's just see the step 3, and how do you decide the why question mark. So if your target value is discrete, the naive version is just majority vote. And it's actually pretty simple, right? So what is this majority vote? It's argmax. It's the argmax. But you can do a little bit different, is not a majority vote. You can just do this equation. I just put it here. This, in fact, give you a prediction is the probability of y question mark big x question mark. So when you have a tie, I mean, there are equal number of like this class 1 versus class 0, and you're going to get a like close to 0.5. So this number give you, it's not just the hard prediction, it gives you some kind of a likelihood flavor. So how likely is this x question mark to be class A, to be class B, to be class 3, so if you have 3 classes. And so it's really just this equation, 1 over k, this k is what you choose, summation over that specific class in your neighbors. So this is a specific J's class. Okay, so they're assuming you have 1 to C different class, so you can use this way, I mean, not just to get the voted classification, you can also get a probability or likelihood of how likely is the potential class for me for that future points. Okay, so let's just see what will k-nearest neighbor learn in this simple example. So we just make a decision for every point, I mean, what are the potential class? And if the point is here, and there's just no doubt will be red, right? If the point is, let me change to blue color. All right, so it doesn't allow me, but that's okay. So this is like, just there's no doubt it's blue. Okay, so the only thing you're going to have doubt are those points you cannot make a decision. And in the classification, and those points that you can make a decision, which similar to the previous page, if you have only 2 classes and the tie case. So those are decision boundary points. Okay, so keep this in mind. You cannot make a decision. In the 2 class case, it's almost equivalent to you got in your neighbor, both contribute the same. And those points, you cannot make a decision. And you can normally just connect those points together to give this curve, we normally call that decision boundaries. And these are extremely important concept in classification. And in this case, you can tell it's a very wiggly decision boundary by the 3 nearest neighbor. Okay, so so I already talked about you can do majority vote if it's discrete. You can do majority vote. You can also do this probability type of prediction. So when your target is continuous, it's actually much simpler, which is exactly the first example we made. You just do summation of your neighbors. So in this notation, I was trying to show it's a summation over all my neighbors. So here, I belongs to neighbor of this specific x0. So this is the y, predicted y for this x0 point. You just consider all the I belongs to neighbor, okay, nearest neighbor set. So this is a set representation. So for all those index points belongs to my nearest neighbor set, I use their yi. I take a summation of the yi, and then over the k, I got the mean. And this is my predicted prediction for the x0. So you can actually tell, and this is also called conditional mean or local mean. All right, so it just the mean of my neighbor, it's me. Okay, to summarize, for the regression, we just average the prediction of the k-nearest neighbors and as the prediction of this future point. And for the classification, we pick the class with the most votes. And for the tie case, if you do not like the tie, you really want to make a decision, there's some kind of trick you can do. For example, this trick. So you can contribute a little bit more for important point. There are actually many tricks you can use, and this is just one of the trick. Yeah. Okay, so this is the end of the first module. I'm going to stop recording.